It turns out there is this hidden, totally invisible math vibrating all around us, literally everywhere. Today in this explainer, we're demystifying oscillations, and we're going to focus specifically on the absolutely incredible physics of simple harmonic motion. We're going to unpack the forces governing everyday motions, zooming in from massive macro concepts right down to the microscopic, invisible physics that make it all work. So if you've ever watched a pendulum swing back and forth and wondered about the hidden clockwork of the universe, well, you are in the exact right place.
Okay, let's dive into this. What exactly does a beating human heart have in common with a vibrating guitar string? I mean, on the surface, they seem completely unrelated, right? One is this squishy, biological rhythm literally keeping us alive, and the other is a mechanical vibration creating music. But here's the secret. Both of these motions are governed by the exact same foundational laws of physics. No, seriously, they both rely on repetitive, cyclical motion to function. And as you'll see by the end of this explainer, the mathematics of a swinging pendulum apply just as perfectly to the strings of a guitar as they do to the cells in your body.
So here's our roadmap for today. First, we'll look at the rhythm of nature. Then we'll define simple harmonic motion, explore the circular motion connection, and dive into velocity and acceleration. After that, we'll cover the restoring force law, and finally, wrap up with energy and constant motion.
All right, starting off with section 1, the rhythm of nature. In our daily lives, some motions are just non-repetitive. Think about a car driving straight down a highway, or a baseball thrown through the air. But for the rhythms that do actually repeat, we need to distinguish between two really key terms: periodic motion and oscillatory motion. So periodic motion is any motion that repeats itself at regular intervals of time. Think of a planet orbiting the sun. It loops around, repeating its path perfectly. But oscillatory motion is a special, much more specific type of periodic motion. This is when an object moves to and fro or back and forth about a mean equilibrium position. Think of that swinging pendulum again, or maybe a boat tossing up and down on river waves. So the key takeaway here is that while every oscillatory motion is periodic, because, it repeats over time, not every periodic motion is oscillatory. After all, a planet doesn't swing back and forth through the sun, right? It orbits around it.
Let's anchor this concept of repetition in something incredibly familiar to all of us: biology. The smallest interval of time after which a motion repeats is called its period, and the number of repetitions per unit of time is its frequency. So if a human heart beats on average 75 times in 1 minute, we can actually calculate its frequency. 75 beats divided by 60 seconds gives us exactly 1.25 oscillations per second, or 1.25 hertz. And if we flip that math around to find the period, meaning the time it takes for one complete heartbeat, we just divide 1 by 1.25. Giving us a period of 0.8 seconds. Every 0.8 seconds, your heart perfectly repeats its cycle.
Moving right along to section 2, defining simple harmonic motion.
Now, what's really interesting about this next slide is this equilibrium position. Imagine a block attached to a spring just resting on a completely frictionless surface. That vertical dotted line right in the middle, that's our equilibrium position. When the block is sitting exactly there, absolutely zero net external force is acting on it. If we just left it alone, it would stay there forever. But if we pull the block away from that dotted line, displacing it by a distance we'll call x, the spring is going to want to pull it back. This creates a to and fro motion, an oscillation, sweeping right back and forth across that equilibrium point.
And here is the beautiful mathematics that perfectly captures that exact motion. Let's break this cosine function down piece by piece, because I promise it's not as intimidating as it looks. X of t simply represents where our block is, its displacement, at any given moment in time. A is our amplitude, so this is the absolute maximum distance we pulled the block away from equilibrium before letting it go. Then we have omega, that little curved W-looking symbol, which is our angular frequency. That tells us how rapidly the system is oscillating. And finally, phi is the phase constant.
Let's talk a little more about that phase element, which is the entire argument inside the cosine function there, omega t plus phi. While the amplitude A tells us how far the block can possibly go, the phase is like the master clock of the entire system. It tells us exactly where the object is in its cycle at any specific millisecond, and whether it's moving away from the center or rushing right back toward it. The phase constant, phi, just sets our starting line. It defines exactly where the block was at the very beginning when our stopwatch was at time equals 0. So we've got this equation built entirely on cosines, which you probably remember from trigonometry are usually associated with circles. So why on earth are we using circles to describe a block moving in a straight line back and forth?
Well, that brings us to section 3, the circular motion connection.
Imagine tying a ball to a string and swinging it in a perfect horizontal circle at a completely constant speed. Now, imagine viewing that spinning ball perfectly edge-on from the side, or even better, shining a light on it and just watching it shadow on the wall. From that side profile, you wouldn't see a circle at all. You'd just see the shadow moving back and forth in a straight line, speeding up as it crosses the center and slowing down right as it reaches the edges. And this brilliantly illustrates the connection. We call it the projection rule. If a particle moves uniformly on a reference circle, its projection, its shadow, on any diameter is mathematically identical to simple harmonic motion. This is exactly why we use angular frequency and pi and cosine functions for springs and pendulums. Sines and cosines naturally bridge the gap between rotating objects and vibrating systems. They are literally two sides of the exact same mathematical coin.
Let's push forward to section 4, velocity and acceleration. By applying just a little bit of calculus to our displacement equation, we basically unlock the whole system. If we take the displacement, x of t, and differentiate it with respect to time, we find the velocity, which, as we know, fluctuates as the object moves, hitting 0 at the extreme outer edges and hitting maximum speed exactly as it passes through the mean position. But here is the real magic. If we differentiate that velocity to get acceleration, the math simplifies beautifully down to a of t equals negative omega squared times x of t.
Look really closely at that equation we just derived. Acceleration equals a negative constant multiplied by displacement. This reveals something absolutely critical. Whatever the value of x, acceleration is always directed towards the center. The further away you pull the block, the greater the acceleration pulling it back. But that little negative sign guarantees it always acts in the opposite direction of the displacement.
Which leads perfectly into section 5, the restoring force law. So the crucial point here is, what happens when we take that acceleration and apply Newton's second law? Force equals mass times acceleration. When we do that, we get the fundamental law of simple harmonic motion. F of t equals negative k times x of t. This is the restoring force. It's a force that is basically completely obsessed with getting the object back to the mean position. That k is just a constant, derived from the mass of the object and the angular frequency squared. For a physical spring, we actually call k the spring constant. The stiffer the spring, the higher the k, and the stronger that restoring force is going to be.
I do want to quickly note that because the force is linearly proportional to x, meaning it's just a simple k times x, we call this ideal model a linear harmonic oscillator. But let's be real, the world is messy. In reality, a force might contain small, additional, complex terms like x squared or x cubed as you really stretch materials to their physical limits. Those are called nonlinear oscillators. But for simple harmonic motion, we're going to stay firmly right here in the elegant, perfectly proportional world of the linear oscillator.
And that brings us to our final stop, section 6, energy in constant motion.
As our block oscillates, its kinetic energy, which is the energy of motion, and its potential energy, which is the stored energy in the spring, are constantly trading places. It's like a perfect handoff. When the block flies through the mean position, it is moving at its absolute fastest, so its kinetic energy is at its maximum. Meanwhile, its potential energy is 0, because the spring isn't stretched or compressed at all. But when the block reaches the extreme edge and pauses for just a microsecond to turn around, its speed is 0, so kinetic energy drops to 0. But at that exact moment, the spring is fully stretched out, meaning potential energy is at its absolute maximum. They just perfectly hand off to one another, back and forth.
And here is why that handoff is so mathematically perfect. If you add the equations for kinetic energy and potential energy together at any given millisecond of the motion, the time variables actually completely cancel out thanks to a trigonometric identity. You are left with the total mechanical energy, E equals 1/2 times k times amplitude squared. No t for time in there anywhere. The total energy is entirely independent of time.
As the source text brilliantly sums it up, in the course of motion, kinetic energy increases at the expense of potential energy, or vice versa, but the total energy remains constant. The universe absolutely loves conservation. In our ideal simple harmonic oscillator, energy is never lost. It just beautifully choreographs this endless dance between motion and tension, forever.
But of course, I have to leave you with a question to ponder. If this total mathematical energy remains stubbornly, perfectly constant, why do playground swings eventually stop? How do real-world forces like friction and air resistance bleed energy out of this perfect math to bring all real-world springs to a silent halt? Well, that introduces the incredibly fascinating world of damped oscillations, and it is exactly where your physics journey should go next.
Keep exploring, keep questioning, and I hope this explainer helped demystify the incredible rhythms moving all around you.